All right, everyone. This is a talk that I've been really looking forward to. A lot of you know Luite. He is the guy behind GHCJS, the shockingly complete and correct GHC implementation for JS. I think I saw a few bugs that he found in GHC while he was creating GHCJS. This is something that I've used a lot personally, both in work and personal projects, and I really think it's a phenomenal project. So give it up for Luite Stegeman.
Thanks, Ryan, for the introduction. I'm going here to talk about GHCJSi today. But some of my earlier talks this year were called Solving the JavaScript Problem, since the problem we have with the web these days, this is not the right button. It's a web-based presentation, I guess, that counts. That's interesting. Well, I can restart it. That's right. All right. So the problem we have with the web is that if we want to do any web programming, we are stuck with what the browsers offer us, and that's basically JavaScript. And these days, when we make larger apps, or whatever we call them, single-page applications, or whatever website with interactivity you have, JavaScript is dynamically typed. The bigger your program gets, the bigger the problem gets. So the way we can solve this, of course, is by not writing JavaScript, but by having something to write the JavaScript for us, which is why I wrote GHCJS. Like Ryan said, it's an implementation of a Haskell compiler based on GHC, obviously from the name. It takes the GHC front end and generates JavaScript from intermediate language. Normal GHC goes from Haskell to core. The optimizer or simplifier rewrites the core to something that's hopefully faster. Then you get STG, which is sort of like core, but a bit more shaped for code generation. Then CMM, which is the platform independent assembly language, and then that you go to machine code through possibly C or LLVM, whatever backend you have, or directly to some assembly code. GHCJS takes the first three steps from that, and it takes over after STG. So it takes STG basically unmodified from GHC, and then translates that to JMacro, libraries on Hackage, which is a sort of simplified JavaScript language, does some optimization on there, and from there it pretty prints the whole thing to a single large JavaScript file, and that's the thing you include in your page, and you run the whole thing. So the front end is responsible for parsing, type checking, and optimization, at least the first step of optimization. GHC also does some optimization on CMM, but obviously since we don't take the CMM code, we have our own optimizer, our own imperative data flow analysis and that variable and branch analysis thing that rewrites the JavaScript into something reasonably sane. There's room for improvement, I'm working on that, but I'll come to that later. So GHCJS has its own binary formats, JS_O files. It has its own package database. It has a split object style linker, which means that if you have a program, GHCJS will start from the main action and trace the whole graph of every function that's reachable through there, or every top level symbol, and it links those in. So you don't need to link a whole library or everything from a library. If you you need a few small things from it, GHCJS takes care of that automatically. And that's just fairly straightforward. GHCJS is fairly closely tied to GHC, but it's still a standalone program. So you install it with Cabal install, and since there's no official release yet, you have to install some snapshot or possibly use Stack to provide one of the predefined snapshots, and then run GHCJS boot to build the libraries like base into the GMP, GHC prim, and also GHCJS a GHCJS specific library for some low-level interaction with the JavaScript environment. And once you've run this, you have a basic GHCJS installation, which looks like a GHC installation with an empty package, or just a global package database with just the things to get started. GHCJS uses GHC as a library, but it wasn't really possible to use it directly out of the box, so we've had to make some changes in the library to make it possible to, say, take the STG code and have the GHCJS code generator take over from there. And there are some extensions in the language, like the foreign import JavaScript extension, which is used specifically to import or interact with JavaScript environments. CCall and the normal foreign function interface is still supported, but it's a bit lower level. It's more like an emulation thing where you can still support existing packages like text or byte string that may have some low-level C code to do some memcopy or some low-level comparison things. And if you write a JavaScript code using the CCall calling convention, you can implement those things, operate on typed arrays, and use the packages basically unmodified. So we had to make some changes in the library to improve plugin support, or at least plugging in other code generators, which is the API hooks thing. I think it's the hooks module in the GHC package. If you look at it, we've had to make some changes to improve rewrite rules and a few other small things for cross-compilation, since GHCJS is basically a cross-compiler. And one of the more recent changes that's related to the topic of today is the external interpreter option for template Haskell and GHCi. It's something that is also related to cross-compilation, but I'll explain in a moment what's exactly changed and how that affects GHCJS. Oh wait, it's in the different order than I thought. Well, the external interpreter is a separation of interpretation of the code and the compilation of the code. Normally when you run GHC in interactive mode, so you start GHC and GHCi or Cabal REPL or whatever, you load a module or you enter some expression at the REPL prompt. The compiler will compile that to bytecode and interpret that same bytecode in the same process that it uses to compile the whole thing. That has some limitations. For example, if you have a cross-compiler, then you can't really interpret code or load code for a different platform, since if you don't have bytecode but other packages, things that you have installed in your package database, then you load binary code from those. And if those are JavaScript, then those won't really work in your native code executable. And there's another problem. If you want stack traces in GHCi, then you have to run your code profiled. And if your GHC compiler is compiled with profiling on, then you could just generate bytecode with profiling information, and you can get your cost centers and stack traces easily out of that. But there's one, massive downside. It makes your GHC compiler extremely slow, since these profiling annotations in the AST, they prevent so many optimizations and you have so much overhead that it makes the whole compiler basically unusable. Well, GHCJS had a solution for this, which had been used for template Haskell for a while and for GHCJSi since this summer, which is having the interpretation of the code in a different process and having a message passing system between the compiler and the process actually running the code. So Simon Marlowe was looking at solving this problem, getting proper stack traces in GHCi and without killing performance. So in the end, in December, he started with the GHCJS code and ported the whole thing and pulled it into GHC. So in GHC 8, there's now the external interpreter option, which if you run it, it will run for GHCi, for example, but also for template Haskell. It will run or interpret the code in a different process, which allows you to do these mismatches between profiling and non-profiling. And in the future, possibly something where you, say, for example, run your template Haskell code on a virtual machine or a CPU emulator or something on a different platform. GHCi still uses its own internal lower level GHC API mechanism through the hooks API that I mentioned before. But I'm going to integrate this again into the code, since it's partly my code anyway. Then we have a common system for running template Haskell and REPL sessions on different platforms and separate from the compiler. That's one of the bigger changes, or more important changes for me. So what I've been working on for GHCJS this year is two things. Earlier last year, the main change was the base library. There used to be a fairly small, very basic library for interacting with JavaScript, and there's now a fairly big library with a string package that works with JavaScript strings but has the same API as the text package, and lots of bindings for JavaScript things like typed arrays and some XML HTTP requests or other basic things that you find in your browser and are just convenient to have a implementation or a binding for at hand. And I've been slowly making progress on the code generator. There are a few things that I really want to improve. One of those things that I've been talking about at ICFP is support for newer features in the newer JavaScript standard. Last year, ES 2015 was standardized or finalized. And one of the important features for GHCJS is that JavaScript finally supports proper tail calls. So if you do a function call in some specific positions in your source tree, then your JavaScript engine is not is required to not grow the stack when you call that recursively. You won't blow the stack if you keep repeatedly calling into these tail calls, which potentially has great benefits for GHCJS performance, since the whole Haskell language is compiled to something where, well, lots of things are tail calls. And for threading, tail calls are also very important. So that's one of the things that I'd like to be able to use if available on some platform. But, well, since JavaScript the whole compiler is something that's made to support what you have on existing platforms, we can't really expect all the existing JavaScript devices to have tail call support within a year or something. None of the JavaScript engines even has a complete implementation of it yet, I think. So one of the projects in the code generator is making it more flexible and making multiple targets possible. And the other main thing is the code size. One of the problems here is that since we work with GHC, GHC does optimization our code, we get STG from that. But the way GHC typically does optimization is by unfolding definitions at the call site and then specializing things. So if you have some dictionary passing for some type class thing and it knows that you pass in the same dictionary, then it can rewrite the whole thing. That's all fine, but for JavaScript it usually means that the code that we start with is fairly big, and that we have lots of repeated small sections that may be efficient, but we still require the JavaScript engine to parse all these repeated things. And I'm trying to figure out a better way to get rid of a bit of that duplication, and at the same time replace the intermediate language that GHCJS does its own optimization on to make the optimizer a bit more effective. Like core, it has type annotations, and the optimizer is completely guided by what types all the terms have. And the current JMacro intermediate language is completely untyped, or at least the variant that I've been using since I stripped the types out of it. So that's helps too. And the other thing is GHCJSi, which is currently a bit of in a prototype status. It works, but the code, some of the modules are basically complete copy-paste from GHC with some changes, and I think it just needs to be integrated properly into the GHC library, and just like the code generator has been with the hooks API. So for this, there may be some changes, and maybe a fork of the GHC library will, in the course of this year, be a dependency of the GHCJS application. Since I think there may be a few changes that will be required, but those should hopefully be merged back into GHC before 8.2, and then the installation time will drop a bit again. But it shouldn't be really noticeable unless you, have to wait for installing GHCJS, which I wouldn't recommend anyway. Anyway, once you have the whole thing booted and installed, it just behaves like GHC. The code that you get, JavaScript code, is a subdirectory, JSX subdirectory, which contains an HTML file which starts the whole thing, which you can load it in a browser. It also contains an old JS file which you can run with Node.js, and you can do various system programming tasks with it. You can read files and start processes and things. And it's the same thing that Cabal uses when encountering a custom setup script with GHCJS. It has to compile setup HS to some executable code. Since it knows how to compile to JavaScript, it compiles to JavaScript and then runs it with Node. So that's part of the infrastructure, and it's been used all over the place, and it's pretty useful. So if you, there's of course Cabal support for GHCJS, there's also stack support. You just supply the --GHCJS option to install some package with GHCJS, or you have a Cabal config file with compiler GHCJS, and it will automatically do that for you in that directory. So it's fairly straightforward to use if you're used to GHC. Like I said, the browser is the main target, or the main reason to do for doing these things, but Node.js is a fairly useful target, and for system programming tasks, if you don't like shell scripting and you can install Node or something, so people have been using it for that, and it's more cross-platform or easier to distribute your scripts that way than with binaries. And what you get is concurrent Haskell, so you have lightweight threading, you have mvars, you have STM, basically the whole Haskell language that you're used to from GHC. And you can also get JavaScript for a function interface, which you write as for an import JavaScript. And then you have some JavaScript expression with placeholders, which you might know from Fay or from UHC. It's slightly different, but it's reasonably convenient, although rather low-level way to talk to JavaScript. And there are several libraries that have a slightly higher level approach, like quasi-quoter, GHCJS, FFIQQ, for quasi-quoting JavaScript, and it will just generate your JavaScript imports automatically. And there's GHCJS DOM, which is a cross-platform DOM manipulation library, which is supported by GHC. You get native code linked against some DOM rendering or HTML rendering thing like WebKit, a native app. And if you compile it with GHCJS, then you can get JavaScript calls to the JavaScript DOM manipulation things. So it's really cross-platform DOM manipulation that way. Well, I shouldn't have done that. So to prove that it works, or what I just did, when I switched to this slide started 10,000 threads. Each thread has a single table cell assigned to it. And it updates the color to some random color, then sleeps for some random time, and then I think, I don't have the code for that here, but it's somewhere in the code for the slides that I'll upload after the talk. So each of these cells has a thread. They sleep for a bit, and 10,000 threads, they're lightweight threads, just like Haskell fork.io threads, and it's really no problem at all for the browser. If I switch away from the slides, it kills all those threads, and now it has just started them again. So there's a tiny delay. So my slides, by the way, have been compiled with Pandoc, and this is generated from some Haskell source code. I just, instead of the curly braces .haskell, I have curly braces run Haskell, and it compiles the thing and gives it an element to run on the page that the slide is on, or that the code is on. And I can just add whatever I want to that slide from that code, and that's what it does. And once you start having fun, you can have more fun. Like you may encounter some samples in the lens library. And this thing uses Gloss, and there's a GHCJS backend for Gloss. So I can play Pong against the computer, and that's it. Just I think I needed to change 2 or 3 lines of code or something in the in the example to make it add the element to this page. But other than that, it's just completely unchanged. And when I switch away from this slide, it kills the threads that run Pong, and there's no performance overhead or whatever in the rest of my talk. So this is kind of neat, I think. And I had this lying around from ICFP and Haskell Exchange, so I thought I'd use it again. But this is not GHCJSi. It's statically compiled into HTML page with a JavaScript file. But we do have a concurrent Haskell runtime, and that's important, since when we want to make a REPL in this setting, when we when we enter expression as a prompt, then the first thing that GHCJS does is compile the expression to JavaScript, since that's what it knows to do. GHCi and GHC also have bytecode for interpreted things, and they have a bytecode evaluator that also supports breakpoints and that kind of things. GHCJS doesn't, and I think not too many people really use this GHCi debugger, so this was just much easier. Just generate JavaScript, run it. But if anyone is really dependent on bytecode and the GHCi debugger, let me know, and perhaps we can edit this in the future. But to get back to how GHCJSi works, first we compile the expression to JavaScript. Then we collect all the dependencies transitively of the expression. So there might be things in your GHCi session, but also things from other packages. GHCJS has the linker, split object style linker, like I said. And it remembers what's already on the JavaScript runtime, so it figures out what dependencies your just entered or just compiled expression has, collects those, bundles them into a bigger JavaScript thing, and then it sends a message to load this code into the JavaScript runtime. That's step 3. And then to start the whole thing, it just asks the runtime to fork IO a thread through the normal Haskell fork IO low-level primitives of the runtime system, and then it runs the code. And often when you have a simple expression, something like say print a 2 + 2 or something, then it will compile to an IO action that prints the result to standard out. The standard out will be taken from the underlying JavaScript runtime, and the result is then just like normal printed to your console. And it just looks like GHCi. It works with external interpreter, so we have GHCJS as the compiler. It sends things to Node.js, and if you don't do anything after starting GHCJSi, then it will just continue, or it will just run your code in Node.js. But if you connect your browser to the Node.js process, it listens to localhost port 6400. Then, if you do that before running your first Haskell expression in your REPL, then the browser takes over. Node.js will, from then on, just act as a gateway. It will forward all messages to the browser, so the browser will run the code, and you have full access to your document and to the things that browsers offer over nodes. But you can't start external processes or whatever Node has that the browser doesn't. So, well, there could be reasons for running both. But what if we have something simple that just prints something to the output and then finishes? Then we're done. But if we don't, if we have, say, some loop or something that takes a while to compute, and we press Control-C on our keyboard in GHCJS, then it interrupts the evaluation of this expression. If we do this in GHCi, I mean, in GHCJSi, it would be very convenient to have the same thing work. And since we do have fully concurrent runtime with all the features that GHCi has, we can actually do this. So what we do is when we press Control break, we just send another message over there. And that message sends an asynchronous exception to the thread that's just been fork-IO'd to run the currently running foreground computation. So your Haskell code gets some kill thread exception or something. It can handle that exception, so perhaps it can do some cleanup or whatever. But usually it would terminate the whole evaluation of the computation and fall back to the prompt. Then you get the prompt back and can do something else. So that's basically the whole message passing protocol for GHCJSi. For template Haskell, the thing is much more complicated since there's reification and type information, but all those things are just managed in the REPL session that runs on the GHC or GHCJS site. So those don't need to be sent over to the browser. So it's actually very simple, and it just reuses many existing components: the incremental linker, JavaScript code generation, and just some threading things to start and stop computations. And to prove that it works, I'm now going to switch to, let's see, this is a bit small, I guess. So you can just start it the same way as GHCi, although GHCJS doesn't install by default some link or some thing to program named GHCJSi, but this works too. So is this big enough? Well, it's fairly boring. I'll switch to the browser in a second. But if I do something like this, then the first time it will take a while to compute. And that's because the linker has figured out that the whole runtime system and a whole bunch of code from the base library is part of the dependencies of the browser or of the expression that I just entered, which is something like print the result of that thing. And it just sent the whole Haskell runtime to the REPL. If I have something, if I do another one, now it's really fast. So it just compiles the expression. Everything else is already there, so it's basically instant. Well, now this session is run by Node.js, so it's headless. I could read files with this thing or do other local system things, but I'll switch to the browser instead. I have to restart GHCJSi for that and go to. And this is hopefully a link to. I think I should have the windows side by side. So so the REPL has detected that the browser has been connected, so the code runs in the browser. So if I run, say, the same thing, then the result is the same, but it has actually been computed by the browser. So I have a demo file with some utility functions or some things to show with some gloss and other stuff, but I think something like this works. No, that's the other way around. Does this work? No. Perhaps I should have. So take 25 of a map. This way. So if I switch to my browser now, then actually it hasn't done anything. And it should have. Perhaps it's a. So this is just something. I had some JavaScript foreign code with some that just adds something to the document, and I can directly interact with the document in my REPL. Let's see. I'll make this a bit smaller. It's still a separate window thing, so there's no user interface where you have everything in the browser. It wouldn't be too hard to change that. I think JS clear body will clear the whole thing again, so you can just interactively play with the whole thing. Like I've demonstrated in the talk, there's a gloss backend for GHCJS. So I think I have something like square, and I think the function I have to set up the thing is animate. Well, this is not really the square that I was drawing. Let's make it red. I think it's C or something. Yeah, I already tried that. That's a bit annoying. Graphics.gloss. Okay, well, I do have colors. Sorry for that. So actually, this is square. And I've done this without explaining what I've been doing. But my animate function, if I start it, I press Control-C all the time when I want to get back to my prompt. So my animate function starts a thread in the background, or in the foreground. It just blocks the prompt. And when I press Control-C, like I explained earlier, the REPL will send an exception to my running computation. This computation catches the exception, removes the gloss element from the document, and then gives you a blank document again and a prompt to, well, start painting on that again. So this is just a really simple user code that does something with the exception. It's animate, but it wasn't animated, so I think I can make it rotate. And I have some other fun things. Something like this, I think. Yeah, no, that's... Oh, I should remove the colors, since then it will actually paint them in different colors. And let's make them a bit closer together. So experimenting with some graphics is... I think I have another zoom. Something like this, so now it will animate the whole thing. And I think if I have something like the individual squares rotate, but yes, I don't know. No, I think I have a few more, but I forgot the names of those things. But it's really easy to work with these things and just have immediate feedback and no dependencies to install other than just the compile, or no, well, GHCJS takes a while to install, but no native libraries or things that are hard to configure afterwards. So, but still, this is all quite fun. But we do have a full GHC REPL session. Sorry for the loop things there. When I interrupt things, there are a few exceptions and things that are not handled quite correctly yet, or it's just some polish problem. But that's why it's not been merged to the main branch yet. So you need to take the GHCJSi branch if you actually want GHCJSi functionality at the moment. And I think I'll eventually, or probably soon, just merge it into main, since people have been using it anyway and are complaining that I don't maintain it as much as the main branch and things. And it doesn't really hinder anything else in the master branch. It just sits there and it's a bit ugly code, but other than that, it doesn't hurt. So, but still, there's a bit of work to do. It's really a sort of prototype status, but people have been using it in production, or at least for development at least. And I haven't heard too many complaints. But anyway, for example, we can also have just bind names. So if we say make an IO ref, and have some value. Now it has to link in a few things. I think I had something like, yeah, IOREF node, and we can refer to R. I think this is just the whole, wait, this returns a thread ID. So what this does, oh, this is really, really small, but this just creates an element that prints the value of the IOREF and updates it. So if I do, I think it's the ref first, and then it immediately updates it. So if I browse or get the type of my R, then or get the type of my thread ID, I can, well, it keeps updating the things, but I can do something like that's a bit, that one. Now it has killed the thread, just silently stops running. There's no, it could have printed something. But if I now update the IOREF, then, well, my element will stay the same. So because this is, I think it's more or less the end of my demonstration, and my talk was called Fun with GHCJSi. I think this is more or less where the fun starts, since I think just like GHCJSi was built from some basic Haskell building blocks, there's really not much new functionality in GHCJS other than importing the interactive session things from GHC. Everything else just built on the concurrent Haskell runtime, the existing linker and stuff. But once we had that, we had the REPL session. But now we have REPL sessions in the browser. We can refer to things. We have a session with things that we can modify. We have threads running in the background. So, well, I think this is where you come in. You find interesting applications for doing these things. For example, if you look at some GSOC project that I did or mentored a few years ago with Shea Arison, he had GHC Live, and if you entered a function or something, or it would, or if you entered some value with a show instance, then it would print it to some web-based interactive GHC session. But if you had a function, then it would have some special instances for the function type, and a function with a double or an integer argument would get rendered as something with a slider that you could use to manipulate the input. It would print the output, and if the output was something other than a text, but say some graphics or something, then it would just render those to the browser. And it's really easy to build those piece by piece by just using standard Haskell components, binding things to names in your session, and build some library out of it. And you just manipulate your threads, you kill them, you keep track of the thread IDs that you need, and that's how you, I think, have fun with GHCJSi. So if anyone has interesting ideas, one idea that I had, but I haven't found time yet to do that, is something like a core-to-core plugin, where if you have constant, a numerical constant in your constants in your expression, then your core-to-core plugin could float them out, have IO refs just the same way as I have IO refs here, or some better synchronization mechanism that actually doesn't have to pull them every so many milliseconds to see if it's been updated. And perhaps render them to input fields or sliders or something in the browser, and have something where you can immediately interact with all the numerical constant in your Haskell code. It would be something like Light Table, but completely user code with GHCJSi. Well, one downside, loading compiler plugins into GHCJSi is a bit tricky since the plugin interface is a bit, it's not built for cross-compilers. So it will try to look in your GHCJS package database, but it should be really reasonably easy to fix that and make it possible to load plugins that way. So if anyone has ideas or whatever, some things may require small changes in GHCJSi, and perhaps like what I said about this GHC Live. The way expressions are compiled and show instances that are needed for printing results, that's a bit hard-coded. It's also somewhat hard-coded in GHCJS, or GHCi, I mean. But it's fairly small and it's fairly simple to change. So I think most things can easily be done here. And if you have something like FRP and you want to interact immediately with something in your FRP thing, you just have to find a name to bind things to things that you can access in your REPL session, and start having fun. And it's just like GHCi. Reloading code is much faster than recompiling code and refreshing the whole page, since the incremental linker keeps track of what's already on the browser, and it only sends the changes when you reload or evaluate some expression. So that's.
And if people do have ideas, will you be around at the unconference over the weekend to help them out with these?
Well, on one condition is that you let me in, since I forgot to register and it's sold out.
I think we can make an exception.
Right. So I'll get back to the conclusion, or to the slides and the conclusion. Like I said, GHCJSi just is a REPL and I think it took me about a week to implement, and a few bug fixes afterwards, but that's basically it. It's not all that much code. It took me a while to figure out how to run everything with native or JavaScript code rather than bytecode. But other than that, it's just reusing all these standard building blocks, which is really great, and it's really shows how good GHC is as something to build on. Unfortunately, as a library, it's not all that great, but in the course of this year, I think we can make it integrate properly. And the browser interface and just interacting with those things from Haskell, I think it's really fun. And just if anyone has any ideas of what to use this, or how to improve the presentation, or perhaps browse symbols in the browser window, or have move the whole thing to a single window, just come to me and or submit a pull request. That's fine too. So that's I think what I wanted to say. So if there's time for questions, then.
We do have a few minutes for questions.
Hey, awesome stuff, by the way. I absolutely love that GHCJS exists and we can actually write, web stuff in Haskell, which is awesome. And I've always, found making UIs like a huge pain point in programming. And so, for some reason, even with all the problems we have in HTML and JavaScript, etc., it still seems to be a really nice way to build UIs. And I think the debuggability of it has a lot to do with it. Like, Chrome Developer Tools really allows us to play around. And I think GHCJSi is awesome in a similar way. But so one idea that I just had about GHCJSi is what if we build something similar to Developer Tools, where you can see all the some kind of elements, again, you have some kind of FRP model or something, and then highlight them and modify them through the REPL. Well, have you worked on actually just trying to put something together? Like Reflex DOM actually is what I'm kind of talk about. But getting GHCJSi actually a core part of the development experience would be really awesome. Just a thought that I had.
Okay. Yeah.
Sorry. I guess I just started rambling. There was a question initially, and now it's kind of lost.
Okay. Well, thanks for the suggestion, at least.
Do you have any plans to support the WebAssembly spec? And if so, what would the roadmap look like?
Well, the problem is that WebAssembly in its current state is, unless they update the spec, something that's more or less equivalent to SNGS with a binary representation, right? So, which is a fairly small subset of JavaScript. You can't do anything that requires objects or anything that does any dynamic allocation. And GHCJS represents the Haskell heap as JavaScript objects. So the JavaScript garbage collector, the JavaScript memory manager, does most of the work for us. There's a bit of additional stuff that we use to trace the heap for finalizers, weak references, and accounting for memory profiling and things, just collecting statistics for the cost centers. But most of this is based on just plain JavaScript objects, so it's basically unusable for that without changing the whole heap representation, which would mean porting the whole GHC memory manager to JavaScript. And at the moment, I have some other tasks that take priority. So probably not soon, unless, and I hope that in the meantime that they will update the WebAssembly spec so we can ship a bit lighter to parse code to the browser, and even though we then still use the normal JavaScript, a superset of the highly optimizable SNGS part, we would still have the benefit of binary distribution and saving that parse overhead. Parse overhead should also improve with the new code generator changes and hopefully getting rid of too much duplication of the inline code in the results. So the whole size should decrease significantly during the course of this year. My goal is to halve the size by May and improve it further later on. But well, I know it when I get there, and it's a bit hard to estimate what the effects of all the changes that I've been making are until it actually works.
Thanks.
Hi, over here.
Yeah.
First off, really great talk. Super interesting stuff. Definitely more of a newbie to GHCJS, so hopefully this is like an easy question. If you wanted to just like generate more or less like a static HTML page with some, inlined Haskell code that then got turned into JavaScript, is there some sort of multi-stage programming like facility for that in GHCJS already, or would you kind of have to like roll your own thing to do that?
Well, the easiest way to do it is by writing your Haskell code to insert its own document under the body tag of your page. So what you get if you compile a program, an executable, is an index, a directory that contains an index HTML file, which includes all the generated JavaScript files and some code to run the main action from your program. And if your main action just builds up the page, then that's easiest. If you don't want to do that programmatically from Haskell, you can just edit your indexed HTML page and it won't override it once it's there. So that's another way to start. And if you want to give a talk and have slides, then you can start with Pandoc and have some inline things with the scripts that I've been using here.
Cool. Thank you.
Love the talk, love the GHCJS. Just curious with regard to bloat and or performance metrics and or heuristics.
Let's see. Performance is best compared to native GHC, and I think in most cases you can expect code to run between 5 and 20 times slower than native code when you compile with optimization on. And there are some things that have worse performance. In general, code that does depend on lots of heap allocation will be more slower than things that run completely unboxed, just doing storing raw values on the stack and things. Those can get just a few times slower. And I think with tail calls we can improve that gap again. Code size, it depends a bit on how big your program is, but it's at the moment one of the bigger problems. So it's relatively easy to get an unminified code size of close to a megabyte or something if you use some smallish libraries. If you use libraries like Haskell source extensions, which is massive, all kinds of inlining, then your code size will blow up by a few megabytes. So don't use that in production apps that you distribute to small mobile devices yet. Maybe it will improve when I can get rid of this duplication, but I don't know how much yet.
All right, we'll take these 3 questions and then move on to the next talk.
So you're a stage in the GHC compilation pipeline. How easy was that to figure out how to kind of hook into that? Was it sort of like all new territory, or was it like, oh, a bunch of people have done this before for other targets?
Well, no one had really done this before since the hooks API didn't exist. So I had to send a pull request to, or not really a pull request, but one of these track tickets and stuff.
So you just had to figure it out yourself,
yes,
what you needed?
Yes, and there were some others who needed similar hooks in the API to, I think, dump some quasi-quoters and some other things. So we got together and got the patch ready for GHC. But it's all a bit ad hoc, I think, since it really depends on the compiler where you need your hooks. So yes, it's all new.
If this is too complicated to answer right now, that's fine. We can just say that. How do you represent threads in the browser?
Threads in the browser. Very simply, all threads run through Trampoline. The threads make sure that they don't take up stay in the code for the thread for too long. They go back to a main loop. The main loop checks from time to time whether the scheduling quantum has expired, and then we'll jump to the scheduler, which may decide that it's time to run other JavaScript or continue to run other Haskell threads. So it will interleave Haskell code and other JavaScript code automatically.
Well, thank you for giving this talk. It was super cool. And also, my question was, when you're dealing with packages like text and byte string, where there's I think you mentioned this to some extent in your talk, was there's like places in there where those are like calling out to like things that are written in C or something like that, and so how do you end up, like, do you have to just like shim those packages out in GHCJS, or how do those end up?
Yes, that's what currently does. So Cabal has some extensions to include JavaScript files with packages that get automatically installed with GHCJS. They get bundled in the big JavaScript bundle when the package is part of the dependencies. But at the moment, those changes haven't been merged upstream yet, since what we currently have also works well enough, and that's just some additional JavaScript file that has an implementation of these C functions in JavaScript, which means they take for a pointer a typed array and some offset into that typed array, and that's where you do your pointer operations. Fairly straightforward to port, actually.
All right, great. Let's give our thanks to the speaker. All right, and one thing I want to add is that this is a huge project that has been almost entirely the work of Luite himself. And so if you're interested in helping to support this project, either by contributing code or contributing money or whatever else, we should talk about it. Luite and I and a couple of other corporate sponsors have been talking about putting together something to ensure that that he can keep working on it full time for the foreseeable future, and also that we can grow the project beyond that. So this is something that Gershom and I and the other members of the Haskell.org committee have been discussing internally for a little while, and it would be great to hear about interest in that. And of course, it's an open source project, and so we should try to get as many people involved as possible. So Luite mentioned that if you have ideas, he can probably help you out over the weekend. But the ideas don't necessarily have to be for your own project. If there are ways that you want to contribute to the project itself, that's also something that would be great to get started on this weekend. So thank you very much, Luite, and we'll get our next speaker up here in just a couple of minutes.